Hi to everyone, my name is Victor Parra and I will be the speaker for this seminar entitled GUI Design and Plan Operational Excellence. I'm a bachelor degree in industrial electronics and for many years I've worked as process control system engineer in the oil and gas and petrochemical industries. I collaborate also with the Spanish section of the International Society of Automation, a non-profit technical society for engineers, technicians, business people, educators, and students who work, study, or are interested in automation. What are we going to talk about? We are going to talk about GUI or graphic user interfaces, or to make it simple, things depicted on the screen that allow you to monitor and to operate your facility. But you probably know it with a different name like operation graphics, mimics, or schematics. Sometimes HMI, human-machine interfaces, are considered the same as graphic user interfaces, but that's just because currently most of the interfaces are mainly graphical. In my opinion, HMI is a broader field that includes graphic user interface but also hardware and software issues, as I depict on the image on the left side of this slide, where you can see that graphic user interfaces are a small part of a bigger field called HMI. The left image shows a typical operation panel before the arrival of the digital control system, or DCS. The right one shows an operation panel implemented in an early DCS. As main differences, we can remark that on DCS, information is not always available anymore, since it must be chopped and compressed to fit into the reduced area of a screen. As a consequence, the previously always available overview of the process disappears. An operator must reveal it when needed by navigating through several operation graphics. In this slide, I wanted to represent the evolution of graphical user interfaces from the 70s to the current days. From middle 70s to early 90s, proprietary operation systems with limited graphical capabilities were commonly used on DCSs. On late 90s and early 2000s, we arrived to the Windows era, a new world full of colors and fancy effects, thanks to the improved graphical capabilities. More data represented on the screen by using more colors, better resolution, more and bigger screen. And this is the typical aspect of a control room on the current days. Here I want to remark that technology evolution has allowed new ways to represent information, but many of the new interfaces imitate the old ones, so they inherit the defects and even make them worse by misusing their extra graphical capabilities. Why are interfaces so important? Well, the first reason is safety. This is a good example. It was a real accident in an oil refinery in Wales that happened in 1994. After 5 hours coping with an abnormal situation due to an important electrical storm, an explosion happened and several fires started. The after-accident investigation made some interesting findings. First, there were good overview graphics. Operators had to navigate through many different detailed graphics to compose an overview of the current situation of the facility. Second, by error, a control valve open in the field was depicted as closed in the graphic. This error was not detected. Perhaps a good overview would have been useful. So, operators struggled to troubleshoot and solve an unreal situation. Third, during hours, operators suffered too many alarms not very clear, so they were working with not very clear graphics in a very stressful situation. As a consequence, you can read it here under the picture, 26 injured, 70 millions of damages plus 0.3 millions of fines. During 2 months, the refinery was completely stopped and the affected area needed 4 months to resume production. The second reason is money, because every action of your operator can cost or make a lot of money. About cost, according to Marsh and McLennan, operational error is the more expensive cause of incident or accident. According to the Abnormal Situation Management Consortium, 42% of abnormal situations are due to human error, sometimes caused or worsened by a deficient interface. According to U.S. Chemical Safety Board, human error costs $10,000 million by year only in the USA. About saving using better interfaces, the Abnormal Situation Management Consortium conducted a study establishing human performance improvement and economic benefit for a human-centered operator interface, an industrial evaluation. It consisted in a controlled comparison between an improved interface, basically a human-centered graphic user interface, and the existing interface in the facility where the study was conducted. 21 professional operators using their planned high-fidelity operation training system faced a series of process upset scenarios previously experienced in the real plant. By using the existing interface and the improved one, operators' performance was better with the improved interface. They were better detecting anomalies and handling abnormal situations. As a result, the Abnormal Situation Management Consortium estimated $800,000 by year of saving just by using the improved graphic user interface. Now we are going to learn a little more about human-machine interaction. The following table summarizes Landberg's findings on this subject. Landberg distinguished three phases, each of them with different goals, typical tasks, and possible problems and difficulties. The first one is called perception and consists basically in data gathering. For example, when the operator navigates through different operation graphics in order to monitor some process variable. Possible problems or difficulties in this phase could be, for example, that data are not observed, either because they are difficult to see, the graphic is not properly designed, or because the monitoring performed by the operator is not good enough. The second phase is called comprehension, and it consists basically in interpret the data previously gathered in the first phase. For example, based on his experience or his knowledge on the process, the operator can detect deviation or unsafe situation. The main problem or difficulty that the operator can find in this phase are due to its excessive dependence on his mental model of the process. The third phase is called projection and consists in forecast and act. Anticipate what will happen next and act in consequence. In this phase, we have also the same main problem detected in the previous phase, and it's excessive confidence in the mental model of the process. If this mental model is not right, probably the actuation of the operator will not be good. Now we are going to talk about some common errors while designing graphical user interfaces. The main one is to forget what the paramount function of an operation graphic is, that is, to monitor and operate a facility. As a consequence, operation graphic become pipe and instrument diagram on a screen with sprayed indication. They are not functional but too detailed. Usually this error is not considered because most of people think that this is how an operation graphic should look like. The second one is that there isn't a design guide, so the entire interface doesn't have an homogeneous style. This is a typical problem in existing plants with many years, because every new unit on or revamping has added a new style or at least some novelties in aspect, but also in the way that graphics are implemented, making maintenance harder. What are the features of a good graphic user interface? There are mainly three. First, it must be adaptive to users' needs at all times. During normal operation, an efficient graphic user interface can perform quite well or good enough. But it's during abnormal situations when their deficiencies becomes more evident. Second, it must make operators' tasks easier in the three phases of human-machine interaction: perception, comprehension, and projecting. And third, it must be easy to learn and use, considering the inherent difficulty of the process itself, of course. And remember, a lack of complaint doesn't mean that you have a good graphic user interface. How to design better graphic user interfaces? From now on, I will give you some tips to improve your interfaces. The first one is to use symbols and standardized templates using an homogeneous style. The reasons are clear, because proceeding that way, the effort required to read and understand the depicted information is reduced, and the actuation is faster, but it also makes learning easier for the new operator. And remember that everything that means the same or works the same must always be represented in the same way, regardless of where it appears. Another useful tip is to increase the amount of information depicted on graphics. How? Well, by using simple design, suppressing all the unnecessary detail that help to save a screen area that can be used to depict more information. Let's look at these two images. The left one represents an operation graphic, a very detailed one. If you try to monitor the process, you'll find it as hard because the process values are hidden among the many details of the graphic. You can see here conduct in 3D effects in different tones of color. You can see the stack, you can see the detail of the electrical motor, you can see also flames, etc. On the right image, all the details has been deleted, depicting process values only, the figures in yellow. You can see how the screen area used to represent process values is minimal compared with the total area of the graphic. Most of this area has been used to represent details that aren't useful to monitor and operate the plant. More about information depicted on graphics. Here I want to make an important remark. When I say increase the amount of information depicted on graphics, I don't mean that you should include more and more data in your graphics, because having data is not the same as having information. Information is data with a context. Sometimes, by simply changing the way data is displayed, increases the information it provides and or make easier to read it. And here you have some examples. These are the results of a blood test. Are you healthy or not? Well, if seen, there is a problem in the second to last row because a red symbol is indicated. Is this value too high or too low? This is solved by adding an extra column indicating the normal range for each of the measured variables. And now, you realize that this value is slightly under the normal range. This is a good representation if you are reading this result at home. But imagine that you are a doctor attending a patient in serious condition. Every second counts. You probably prefer this other depiction because it's easy at a glance to know what's wrong. Another example. These special gauges. These symbols are usually included in special object libraries for the industrial control system provided. Different shapes are used depending on each type of variable. They include indication for normal operation range and alarm. Another example are the radar, spider, or star chart, ideal to represent at the same time several related variables. Another example, trends. They are used on existing graphic user interfaces, but usually on specific graphics. They are very helpful to improve projection phase if they are included in common graphics. Another useful tip is to create overview and oriented to specific operation graphics. And these are two examples. This graphic is a special one designed for the startup of a unit. It summarizes data coming from 12 different graphics. So this is the only graphic that the panel operator needs to monitor the startup process. This is another good example. It's an overview graphic of a process unit. It summarizes the main data required to monitor how is running the unit. These kind of graphics are a good way to present the advantage of this new way of graphic user interface designing. So it's a powerful tool when you are trying to sell your job, improving the interface. Another useful tip is to create graphics with different levels of detail. Common interfaces usually have only a level of detail. Consequences are a bad overview of the process and coded graphics. We recommend 4 different levels as depicted in this image, going from level 1, the less detailed one, to level 4, the more detailed. Level 1 and 2 are similar to the overview graphic that we have seen in the previous slide, while level 3 is the level of detail of the common operation graphic in the current graphic interfaces. Level 4 are graphics reserved to show helpful information, not always needed to operate. For example, for diagnostic, interlocks, first outs, procedures, details, documentation, etc. More about a graphic of different level of detail. This is an example of a level 1 graphic with an overview of the entire plant. In this case, 5 different lines of production. This other represents a level 2 graphic. In this case, is an overview of one of the 5 lines of production. Functional overview graphics are better than schematics one since they allow to summarize more information, because you save area not representing lines or equipment, and all that saved area can be used to add some extra information and represent data, for example, in form of trends, graphic bars, etc. Those are examples of a level 3 graphic, probably very similar to the one that you have in your facility, and a level 4 graphic. In this case, is a helpful pop-up screen showing how it works and a control loop, in this case a split range. Another aspect to consider to design better graphic user interface is to improve the navigation among graphics. This image represents 2 different possible navigation schemes in a graphical user interface with 4 level of display. The option on the left is not recommended because for going from A to B obliges to 1, 2, 3, 4, 5, 6 click. You have to pass through 6 different graphics if you want to go from A to B. This is while the recommended scheme of navigation take only 1 to 3 clicks to go from a graphic to another one, just because this graphic allows to go quickly from one to another. User must be able to change quickly among related graphics without too many clicks. This is an example of this. This is an overview graphic, and the button added at the bottom give a quick access to other related graphic. You can see it as, for example, we are here in a second level graphic, and each of these buttons give access, a quick access to the graphics in the level 3. There is also a button that allows you to go to the level just up to this one. It is also a good idea to provide a representation of plank hierarchy, because that way you can quickly go no matter to what graphic you need. Now we will talk about colors and effects, a complex issue that will require several slides. We will start with some basic recommendations. The first one, use a minimum of color code but consistently across display hierarchy level. Why to use many different colors if eventually they are so similar that are difficult to distinguish? Second, ensure that color codes avoid conflicts with cultural stereotype or industry standard. Each color has an associated meaning. For example, red is used to indicate danger, alarm, prohibition, abnormal status, etc. While green means okay, permission, normal status, but this meaning depends on cultural stereotypes or industry standard. An example of cultural differences. In Western countries, the color associated with mourning is black, while in Eastern countries is white, like the case of India, or orange, in countries where Buddhism is the majority religion. About industry differences. In oil and gas, it's common to use green and red colors to indicate equipment running and equipment stopped, respectively. However, in power generation, the meaning of the color is just the opposite, because they understand that the equipment running under tension represents a risk, so it's depicted in red color. Third, color used to indicate alarm shouldn't have any other use. According to the Center for Operator Performance, it takes up to 25 longer to detect an alarm when the color red is also used to indicate the status of valves and/or motors. More about colors. Color perception is not the same for everyone. Consider not only anomalies as color blindness, but also age. The ability to differentiate colors worsens with age. It's also different between genders. Generally speaking, men's color perception is worse than women's. Knowing that, try to avoid color combinations that are confusing for colorblind perception. Ensure that color combinations provide acceptable and sufficient contrast. Use a display background color that maximizes the overall readability without causing unnecessary eye strain or fatigue over time. More about color. This is a rule of thumb easy to understand after the previous slide. Don't rely on color alone to code information, and ensure that color is a redundant visual coding of information. This image show a couple of examples of good and bad color coding. The first example is about PAM status. The common and wrong way to proceed is indicated in the left side of the image, where PAM not running is indicated in red and PAM running is indicated in green. Why this way is a wrong way to indicate PAM status? Just because you are relying only in color and you are using color usually reserved for alarms, red and green. This is a better way to represent the same information. In this case, the PAM stopped is indicated in dark gray and with a text indicating stop. The PAM running is indicated in white with a text saying running. Below, you'll find an example related to alarm. In the upper side, you'll see that different alarm priority are indicated with color. Red for priority 1, yellow for priority 2, orange for priority 3, and pink for diagnostic priority. Why this way of representing this info is wrong? Just because rely only on color. This second option is better because alarm priority is indicated not only with color but also with shapes and figure. So for example, priority alarm 1 is indicated in a red square with a 1 inside. Priority 2 alarm are indicated with a yellow triangle with a number 2 inside. Let's talk about effects. Here the rules are simple. Use brightness coding sparingly for silence coding. If you use it too much, it could cause unnecessary eye strain or fatigue. Effects should be reduced as much as possible or discarded completely as they are too distracting. Anything displacing, spinning, or blinking on a screen, like the avocado exercising on the top right corner, attract operators' attention. The blink option should be used sparingly, typically for alarms only. Well, we are arriving to the end of this presentation. This slide compiles some standard recommendations and good practices to follow while designing graphic user interfaces. As far as I know, none of all of them are mandatory, but are recognized as good practices. About working with computers and other interactive systems, not specifically industrial system, we have these references, some ANSI and ISO guides, and also new. About specifically about graphic user interface design and industrial environment, I can recommend some references from the American Petroleum Institute, the Abnormal Situation Management Consortium, the Engineering Equipment and Material User Association, the International Society of Automation, an organization that I usually collaborate with, and the German Association of Engineering. And this is a compilation of tips for successfully improving your graphic user interface. First, you should give a graphic user interface the importance it deserves. We have seen how it affects to the operational excellence of your facility. Before drawing, establish a style guide and the library of symbols to be used. It's strongly recommended that you use the symbols provided by the control system provider. It's a good idea to involve user from the very beginning. That way, you can know about their needs and their common tasks. And it's also a way to let them know what you can offer with the new interface. Another tip, change things. Don't emulate only the old interface. Add value. And the last one, test the new interface because if user find an error, they will lose their confidence in the new interface. And these are some of the references that I've used to elaborate this presentation. I hope that you have found it interesting, and many thanks for your attention.